Yeah, our last presentation for this afternoon session is from Saswata Dasgupta. He's from Paisani Research Group from University of California, San Diego. So welcome, Saswata.
Okay, so thanks for the introduction, and I hope all of you can see my screen. My name is Saswata Dasgupta. I'm a postdoctoral researcher in Professor Francisco Pozzani's group at UC San Diego. And today I'll be talking about the stuff we did for last couple of years, and we are still bending up upon the lessons we have learned so far. So I'll be talking about the data-driven many-body potentials from density functional theory and many-body approach to QMMM simulations. So one of the biggest challenges to the QMMM is basically there is a energetic discontinuity which exists in between the QM and MM boundary. And that discontinuity comes because there are different physics associated with the QM and MM region. And due to this energetic discontinuity, it gives rise to unrealistic forces in the boundary, and also it leads to various erroneous behavior into the structural and dynamical properties. One way to deal with this problem is introduction of a transition layer, which somewhat alleviates this problem as it smoothens the QM energy with the MM part. But it also comes with a trade-off of computational expenses, because now you have to take care about all the various possible QM and MM interactions with each other, and you need to average them out. So basically, it's computationally way more expensive. And not only that, still the system is undergoing, or the system is observed under two different potentials, because your QM, the potential you get from the QM and MM are completely different. So another way to deal with this problem is, suppose we have a MM force field whose accuracy is pretty similar to the QM method we are using, suppose density functional theory. So what we can do, or what we have done, we have developed a bunch of data-driven potentials which are based on the density functional theory, which with minimum loss of accuracy, it can successfully describe the MM part. So essentially what you can do, you can actually describe the QM and MM part approximately under the same Hamiltonian. So I'll divide this talk into three different parts. The first part, I'll be talking about the framework of MB-DFT, or how we develop the data-driven many-body potentials from density functional theory. So as Dustin mentioned in the morning session, we can write the overall energy of a system as a sum of different many-body contributions. So just like this water cluster, you can write it as a sum of different one-body contributions which are coming from the distortions of your monomer, or the distortions of this water molecule in this example. And then the two-body term essentially takes care about your interaction in a dimer. Similarly, the three-body term is the interaction you have in a trimer, and so on and so forth, and you can go up to n-body. And if you add all these pieces together, you get your exact overall energy. Now, for density functional theory, in case of water clusters and various other aqueous systems, what we have observed, the two-body and three-body energies make up to 95% of the interaction energy. And the four-body and higher order term only governs around 5% of your overall interaction energy. So in the MB-DFT formalism, we can approximate the four-body and higher term with a classical polarization, and we can explicitly describe the first three terms, or in other words, the one-body, two-body, and three-body. So here is kind of a flowchart how it works. So we build the training sets, suppose for this water, different one-body, two-body, and three-body training sets, and we feed the overall energetics with the permutationally invariant polynomial. And after fitting the permutationally invariant polynomial, we get the one-body, two-body, three-body terms, and along with that, we add the classical term, the polarization and the electrostatic, which completes the development of this polarizable force field. On that note, I want to mention this is not only true for water. You can build different many-body potential by yourself if you use the MB-Fit software developed by your group. But the only thing is the system needs to follow the many-body approximation. So you will generate the configurations using the harmonic quantum partition function. And using a QM calculator, so far the QChem and Cypher are two possible options, but it's really easy to make room for other electron structure code. And then you build the configurations, calculate their energies, and feed the polynomials and splice everything to the MBX to run the dynamics out of it. So by doing that, we actually developed a bunch of different MB-DFT potentials coming from different DFT functionals. And the main reason of that is, suppose we want to do a QMMM calculation, we want to be prepared so that for a corresponding density functional, we should have a MB-DFT potential available. So basically, we made this whole buffet of MB-DFT potentials. And on the left-hand side, there is an example of how this MB-DFT potentials behave. So basically, here we have shown the error between the MB-DFT potential with its parent DFT functional for the prism isomer of water hexamer. And as you can see, the errors looks pretty reasonable, especially the 1-body, 2-body, and 3-body errors are pretty small because they're data-driven. They're fitted with the permutationally invariant polynomial. But we need to be careful because certain MB-DFT potentials, especially this PBE, shows a surprisingly high error for the 4-body or higher term. Now, it might seem not that much because it's only around 1 kcal per mole, but we need to remember for this water hexamer, these energies are really pretty small. The 4-body energy is pretty small. So 1 kcal per mole error is actually a lot for this kind of systems. Just to bolster my claim, here, let's see how the MD simulations using this potential look like. So here we have the MB analog of the REF-PBE-D3 functional, which is basically a variant of the vanilla flavored PBE. And we also have a much more well-behaved B97 MRV functional. When we run the NVT simulations with the MB-DFT-PBE-D3, we see a much more structured liquid water compared to the experiment. Also, if you compare the tetrahedral order parameter, that also supports the claim with respect to MB pole, which is fitted with couple cluster data, it gives a way more structured liquid. On the other hand, the well-behaved B97 MRV is much better and pretty close to the experimental observation from the radial distribution function point of view. And also it is very close to the tetrahedral order parameter you obtain from MB pole. Now that brings me to my second part, which is how we can improve this accuracy for the density functional approximation, as well as our many-body potentiality functionals with this DFT functional. So let's just take a step back and let's revisit what are the associated errors in DFT. So in a DFT functional, we can have two different kind of errors. One is the functional driven error, where the error is coming from your choice of the density functional approximation you're doing. And the second part is known as the density driven error, which is essentially the energy difference between your approximate density and the true density. And this density driven error can be divided into two subportions. One is the one electron self-interaction error, where the electron is interacting with itself, and another is known as the many electron self-interaction error or the delocalization error, where the energetics of the system deviates from its piecewise linearity as you add a fractional electron. The wave function based theory is essentially free from this one electron self-interaction error because the Coulomb interaction only governs for two particle interactions and it's pairwise additive. So instead of having the self-consistent DFT density, if we use a density coming from wave function based theory non-self-consistently from something like Hartree-Fock theory, we can actually solve somewhat this density-driven error problem. And that method is known as the density corrected DFT or DCDFT. So what we do, we essentially calculate the energy of the density functional with a surrogated density coming from the Hartree-Fock theory. And by doing that, it minimizes the amount of density-driven error we have. So let's revisit the problems we have discussed previously. As I mentioned, the potential coming from the PBE-D3 has large four-body error, and that's kind of unrealistic. But by doing this density correction and making these models, which we call the MB-DFT DC, we are actually making this error, or we are actually minimizing this error by a factor of half. And here we can see the prism, cage, and book one isomer. For all of them, the four-body error is reducing significantly when we feed the MB potential with the density corrected PBD3 data. Now, about the liquid water simulation, you can see there is a contrasting improvement coming from the density correction, as now it gives a much more realistic water structure, both in terms of the radial distribution function as well as the tetrahedral order parameter. And not only that, another thing to mention that, as we have already mentioned, or we are kind of expected, that B97 MRV has smaller density driven error compared to the FPB-D3. So the amount of improvement for this functional in case of the liquid water's radial distribution function or the tetrahedral order parameter is pretty small. Now, SCAN has been really popular to study the condensed phase in recent years, especially because SCAN satisfies all the 70 necessary constraints thrown at a meta-GGA functional. Definitely, it makes SCAN a pretty good functional, but it is still prone to the density-driven error. And due to that reason, it lacks the reproducibility in case of the quantitative agreement. Just to revisit the literature, what we can see here on the top, we have the interaction energy for all the water hexamer isomers using SCAN and different SCAN variants from SCAN to SCAN 0 with varying amount of Hartree-Fock exchange. And the red curve on top actually designates the couple cluster value. So you can see, although you're adding a fraction of Hartree-Fock exchange, but the energy gap is still pretty large. And if we do a many-body decomposition of these SCAN alpha functionals, we see that majority of this error is coming from the two-body part. So for all of the isomers, the significant error is coming from the two-body. Different groups, including our group, did develop different potentials based on the SCAN or SCAN alpha functional with varying amount of Hartree-Fock exchange. But none of them really reproduce the water structure with a quantitative agreement with the experiments. And that hinders the progress of SCAN functional. Now, as we have seen in the previous slide, the SCAN is way off from the couple cluster results, and adding a fraction of Hartree-Fock exchange improves it for some of the isomers, just like here we can see it improves it for the prism, cage, or somewhat for the book one isomer, but then it deteriorates for some of the other isomers. Now let's see what happens if we do a density correction on the SCAN and SCAN 0 functional. By doing a density correction on SCAN functional, we see that the density corrected SCAN sits on top of the couple clustered result. And that's surprising, but one way to explain it is basically when you nullify or minimize the density-driven error, as SCAN satisfies all the 70 necessary constraints, it makes it a pretty good functional when you remove or minimize these density-driven errors. On the other hand, you can see SCAN 0 with the density correction improves, but the improvement is not as significant as it is observed for SCAN or the DC SCAN. And if we do the whole many-body decomposition for water octamer isomers, we see the significant contributor two-body error is getting negated by doing this density correction, and it gives you much closer interaction energies of the many-body decompositions with respect to the couple cluster results. And not only for neat liquid water, you can actually check this for different other water clusters or different other non-covalently interacted systems. Here, I have given 4 such examples. We have the protonated water clusters, the deprotonated water clusters, the alkali metal clusters, and the halides. And for all of them, we are comparing the energy of the scan, DC scan, along with the Flossig variant of scan. The Flossig is essentially the second generation of the Pardue-Zonger self-interaction correction with Fermi-Laudin orbital, which removes the self-interaction error in an orbital by orbital basis. And for all of them, you can see scan, the density corrected scan outperforms the self-interaction corrected scan version. And it gives you much better results and much more consistent results for all of them. So essentially, scan goes pretty close to the couple cluster value for this aqueous system. And we decided to build a force field based on this DC scan. And we are calling this model as MB-Scan DC. And here you can see the many body decompositions using this MB-Scan DC with other scan variant. And as expected, the 2-body energies with this MB-Scan DC is pretty close with its parent DC scan counterpart. The 3-body errors are also pretty small, and the overall interaction energy is pretty close. So using the MB-Scan DC, which is a polarizable force field, we are actually going very close to the couple cluster energetics obtained for this water isomer hexamers. Now, how about the liquid water? Here we have compared the liquid water structural properties compared against the MB-Scan with the MB-Scan DC, and you can see the shaded region is our experiment. And we have also compared the many body analog of the DM21 functional developed by DeepMind, which claimed to be essentially free from the self-interaction error. And for both of the radial distribution function and tetrahedral order parameter, you can see the MB-Scan DC overlaps with the shaded region, whereas the MB-DM21 is not bad, but it's still not as reproducible as the MB-Scan DC results. Now, if we just want to compare the density and self-diffusion coefficient, we can see the MB-Scan DC gives us the proper parabolic behavior observed in the experiment or the MB-pole simulation. And you have the maxima very close to the 277 Kelvin. On the other hand, the scan-based potentials are way off, and it gives you a kind of like a sigmoidal behavior, and it gives you a completely wrong description of your density. The self-diffusion coefficient using the MB-Scan DC also overlaps with the experiment and the MB-pole results, whereas the scan-based neural networks are a bit off. Now here I want to give a disclaimer. So far we have described, okay, for all the cases, for all the many-body interactions, the density corrected scan outperforms the scan. But we never compared anything for the one-body energy or for the monomer distortion. So here we have a 2D contour plot for both scan and DC scan, and we compared the error with respect to the couple cluster. But surprisingly, you can see for this one, the scan has a much more stable value than the DC scan. The DC scan has higher error as you move away from the equilibrium position, which essentially tells us the density correction is a very good approximation for non-compact system or like hydrogen bonded system. But for a compact system like water monomer, the scan gives rise to better density than the Hartree-Fock. So we need to be careful when we are doing this kind of calculations. And this leads me to the third part, which is the many-body approach to the QMMM simulations. So far, all the potentiality functions we have described, they're pretty good and pretty accurate and kind of successful to reproduce their DFT counterparts, but they cannot make or break bonds. If you want to simulate a chemical reaction in condensed phase, you cannot do that with these polarizable force fields. So we need to take the help of the QM-MM kind of approach, where the QM part will take care about the reaction, where the reactant and bunch of the water molecules will be a QM part, and the rest of the things will be approximated by the MM atoms. And how we're doing it, as these MB-DFT potentials are polarizable. So we are taking a fully polarizable approach to this QMMM method. So basically, our QM and MM part, they both can cross polarize each other, and the charges and dipoles in the MM region is essentially coupled with the electronic density in the QM region. And your overall variational energy functional can be divided into three parts. One is the QM energy functional we get. Another is the classical part, which you get from this MB-DFT potential. And the third one is the coupling between the QM and MB-MM. So this variational energy functional can be written as a QM functional plus an environmental term, which is basically which absorbs both the coupling term as well as the classical part. And this QMMM coupling can be also subdivided into two parts. One is the electrostatics, and the other one is the polarization. And this electrostatics you can calculate for this MB-DFT potentials. As these potentials only has fixed charges, you can actually calculate the interaction between these fixed charges and the potential generated by the QM density at this MM atoms, which is given by this equation 3. And the polarization energy in this fully polarizable framework can be written like this, where we are getting this induced dipoles from the MM driver, which is MBX in this case. So the full workflow somewhat looks like this. So you start the initial condition, calculate the classical contributions, then you start the calculation with the QM code and generate the fully relaxed density matrix and the Fock matrix. You read the MB-DFT fixed charges and the coordinates, and then you calculate this electric field at each of the MM position. Then you feed that data to the MBX, which then calculates the electrostatics for you, and it gives rise to the induced dipole, which we need to generate the updated Fock matrix, which is basically added as a perturbation. And then we solve this SCF equation, we calculate the energies and forces, and then we propagate the trajectories using that. The developments are currently ongoing for QChem, and we have started the development for the Quick, which is a GPU enabled code. And just to give you an example of how powerful this QM-MB-MM method can be, or why it is so exciting to us, here let's take this example, which is basically done by our group in collaboration with Professor Liparini and Professor Cisneros. So what we see on the top, we have what you have on the top. It means you start with 1 QM water and 5 mm water, and then you exchange the QM and mm water, and in the very end you have 5 QM water and 1 mm water. And in the top panel, you start your QM part with the PB0D3, and the MM part is basically MB pole, which is fitted with the couple cluster data. So your QM and MM part essentially have two different accuracies. So you can see clearly that as you add more and more water, or as you exchange the water between the QM and MM region, it is starting to drift downwards, because the PB0 is giving you a more overbound structure because of its self-interaction error. The curve is going, or these violin plots are going downwards. On the other hand, in the bottom panel, when you have both the QM and MB region approximately coming from the same Hamiltonian, or in other words, when the QM region is PB0D3 and the MM region is MB-PB0D3, now your energies are kind of pretty stable with the exchange of this water molecule. And this tells us two things. The first thing is, as we mentioned about the transition layer, we can actually get away without having a transition layer for this kind of things. And the second thing is, if we want to do adaptive QMMM, we actually, if we are careful about choosing our functional and corresponding MB-DFT potential, we actually don't need the buffer region in the adaptive partitioning, because here you can see with the exchange of these waters, and as you are increasing the size of the QM region, you're kind of having a stable energy out of this whole water prism hexamer. So to conclude everything what I talked about, the MB-DFT potentials coming from this DFT functionals achieve high accuracy than the regular polarizable force field, and it quantitatively reproduces each individual term in your many-body contribution. And for the traditional functionals, the DC-DFT helps to remove the density-driven errors, so elevates its overall accuracy, not only in case of the MB-DFT potential, but also for the density functional approximation. And the MB-scan DC correctly describes the properties of water all across the phases, starting from the gas phase water cluster to the condensed phase simulations at the cost of the advanced polarizable force field. And the fully polarizable QM-MB-MM approach helps to remove the energy discontinuity, and probably that will also help us to get away without having a buffer region in the adaptive partitioning. And with that, I would like to thank Terry and Etienne, who have been an integral part of this project. I would also like to thank my PI, Professor Francesco Pazzani, the whole Pazzani lab, QChem and MBX, DOE for funding, and SDSC for computer time. And with that, I'd be happy to have any of your questions.
Thank you, Saswata, for your amazing presentation. So the floor is open for your questions. So we have one question on the chat. So we can start with this question first.
Yeah, so the polarizable force field of this MB-DFT force field we are developing from the DFT calculation. So as you see here, we are actually fitting the one body, two body, and three body term from the DFT calculations, or in other words, energies, and then we are adding the classical terms. So the polarizable force field is essentially this MB-DFT potentials, or whatever we are getting from here.
Okay. So, thank you, Saswata. So we have any other question for Saswata?
I have a quick question.
Yeah,
great talk. Actually, very interesting idea that you can potentially get rid of this healing region, right? That people use in adaptive dynamics, where you have this buffer region. But then I wonder, in MB-Pol, you have short-range polynomials, or
so we need
polynomials for the also for the repulsive interaction between molecules too close to each other. So what happens to a molecule that crosses the buffer region? How do you, if you get rid of that buffer region, at some point you switch on these polynomials, right? Or at some point you switch them off. How do you handle that?
So probably, I mean, that's kind of an early stage question. So we need to do some benchmarking depending upon the size of the QM region, first of all. I mean, we need to check whether if you're taking too small QM region, probably that might hinder actually with the polynomials we have for this MB-DFT potentials. Also, another thing we need to see, like how these polynomials affect the overall energetics of this QMMM. So these are kind of open-ended questions we need to benchmark. But so far for this water hexamers, which is kind of a very toy system, what we have seen, it actually works pretty well. So we will see what happens if we just increase or decrease the system size. And probably at some point, we need to reparameterize this classical functional forms for this MB-DFT potential. So when we introduce a QM region, so that's we need to explore.
Right. So can I follow up quick? Just very quick.
Yeah.
So I think, you still need to switch a QM molecule to an MM molecule if the water goes away, or switch the MM molecule to a QM molecule, right? So you still have to somehow switch this, two calculations, one where you have the QM molecule, one where you have the molecule being MM, and then kind of a linear mixing, right, as the molecule phases out.
Yes.
But
No, wait.
what you're
Sorry.
saying is, I guess what you're
Sorry,
saying
can
is
I,
okay, go ahead.
can I say, I don't think at the moment there is this. I mean, at the moment, the cross term between the QM and the MB part is done through the polynomials. So the polynomials are active between the AQM molecule and the non-QM molecule.
Right, but then what happens when an MM molecule, when a QM molecule becomes MM? You switch those on?
No, it's already on. That molecule is already coupled with a short range polynomial.
But I guess I'm asking about the QM-QM interaction at that point. Imagine one of the QM molecules breaks off and becomes an MM molecule. What do? You switch on directly the polynomial? Okay, I see.
Yeah, at the moment, the calculations for the hexamers have been done that way.
Okay,
and the errors, I mean, the deviation is very small, which
small,
means that probably with the term, of course, the energy is not strictly conserved, right? But if you use the thermostat, it should be okay.
Yeah, makes sense.
Okay, so thank you, everybody. So still we have 5 minutes. We have another question in the chat. I don't know if you can see the questions as well on the chat. If no, I can.
Oh, yeah. Okay, so the thing is, here we are comparing the error between the MB-DFT with its corresponding DFT counterpart. So yeah, Blip definitely has lower error when you compare their energies for the MB-DFT with the DFT part. But if you compare that with the couple cluster, they both are pretty bad, and there is a error cancellation in case of PB. So if you just, I don't have the data here, but if you just follow this paper, we have actually computed the gas phase properties as well as the liquid phase bulk simulations using Blip D3 as well, and they are also pretty bad, and they give you the overstructured liquid out of it. So here it's kind of deceiving because we are not comparing it with couple cluster, but the couple cluster results are somewhere in the SI of this paper. So if you just check that out, they're also pretty bad and give you way more overstructured liquid.
So I can comment a bit on this and add to that question. So what might be confusing is that if for a set of water clusters, right, you compute the interaction energy, BLIP compared to PBE looks like it's more accurate, right? It's going to have a less error relative to a reference that you may use like coupled cluster. But here, part of what Saswata was presenting was in context of the functional driven errors versus the density driven errors. And so in general terms, the accuracy that you see for a functional computing these energies is going to be that balance or that cancellation between those two. In the case of BLIP, when we removed the density driven errors, then what we did was effectively expose that the errors due to the functional are actually quite large, and that for that functional made it like a make or break case, and that's what led it to have significantly more error in once you did the DC compared to PBE, but not before.